Hi, I'm Hideki Takase from Kyoto, Japan. This is second time to attend the Elixir conference. First time is Lone Star ElixConf on this year. So nice to meet you, or long time no see. It's my big pleasure to present our work on Elixir conference. Thank you so much to accept my talk proposal. So I am an assistant professor at Kyoto University. My major research interest, research topic is system-level design methodology for embedded real-time systems, especially for co-design about processors and FPGA. And also, I surely have a great interest about Elixir for IoT, especially for Nerves project. So, first of all, let me introduce my research collaborator. I would like to say a big thanks to Kentaro and Yasuhiro. They are my students in laboratory, and they have made a great effort on this project. I appreciate the member of Fukuoka EX. Do you know Fukuoka EX? Only one? It is an Elixir community in Fukuoka, Japan. They always give a technical support for me. As you may know, Zaki and Hisaue will present their work on tomorrow. Their work is about GPU with Elixir. Don't miss this opportunity. I also appreciate the member of HLS Friends. It is a Japanese community for self-made high-level synthesis tools by various programming languages. These members give useful comment and motivation to my project. So I will start my presentation. My presentation consists of 3 parts. How many people do you know the FPGA? Oh, almost. So first part is just a lecture in the university. So I will introduce about hardware design and FPGA quickly. First topic is traditional computing resources. There is 2 resources, processors with software and hardware, ASIC as hardware. Processor is a resources which can do whatever you want. To cover all requirements from software instruction, processor has universal data passes, fixed data width, and arithmetic units. On contrary, hardware can do immediately as what you need. Since hardware is designed to specific requirements, internal architecture is fixed and it has dedicated data width and customized operation unit as needed. There is pros and cons between software and hardware. For hardware, performance and power efficiency are much better compared with processor, because hardware can be operated as the demand. In addition, high-performance parallel processing can be realized easily if we can design hardware carefully. On the other hand, one of the advantages of processor with software is design flexibility. We can realize various applications respective to your programming. So FPGA takes good advantages from both resources. It means that FPGA is better performance and power efficiency than processors with better design flexibility. So I introduce what is FPGA. FPGA stands for Field-Programmable Gate Array. It is LSI whose contents can be changed anytime as you want. So we can realize the unique digital circuits on FPGA. There is two major vendors, Xilinx and Intel Altera. As shown in this figure, internal architecture of FPGA is expressed as a systolic array of logic block, connection, switching, and I/O blocks. The logic blocks consist of lookup tables and data flip-flops. So we can change the hardware behavior by deciding the value of LUTs and their connections. This is a common data flow for hardware design on FPGA. Hardware description languages, HDL, is used to design the hardware. We should design the behavior of circuits at register transfer level, such as always block and blocking and non-blocking statement. But it is difficult to design by HDL to hardware since its abstraction level is very low. When we have finished the design of hardware, we will check the hardware design by register transfer level simulation like this. We should verify the design at cycle level behavior. These are very busy work. And then we should apply logic synthesis, technology mapping, place and routing. However, don't worry because EDA tools can support almost these steps as software compiler. Finally, bitstream, it is an image file for burning to FPGA chip. Bitstream can be derived by EDA tools. So next is how to use of FPGA. FPGA is typically used with processor as an accelerator. We can offload the part of heavy processing on processors to the FPGA. So we expect the performance improvement and power savings by utilizing FPGA. To communicate software and hardware efficiently, we need the suitable communication interfaces. So applications of FPGAs is as follows. As an application of FPGAs, it was formerly used for rapid design of ASICs. By using FPGA like this, functionality can be verified before the production of ASIC. And more, software developers can start their work before hardware manufacturing is finished. Recently, FPGA is used for the final product. It is possible to have a rewriting function after shipping. Recently, practical applications of FPGA are financial market transactions, robotics, and automotives, data center, cloud center, and machine learning. I think you like machine learning and AI applications. Structure of neural network is often expressed as the array of numbers. Please remember that the structure of FPGA. FPGA's systolic array architecture is suitable for the structure of neural network. So neuron synapse value flow through the pipeline as a circuit. Advantages of FPGA is first, various systems can be designed onto one LSI. And also, high performance and low power savings can be realized to use the FPGAs. One of the most important advantages of FPGA is parallel processing can be realized at task and data levels. Data stream processing can be realized easily on FPGA. I want to share the current technology trends of FPGA. First trend is the increase in circuit scale and amount of logic block. It means that high-performance systems can be realized, and further increase will continue by new technologies. Second trend is tightly coupling with processors. In the general-purpose domains, connection via PCI Express to processors with FPGA is commonly used. In the embedded domain, integration with embedded processors such as ARM Cortex processors becomes popular. However, these trends causes the problem. High-quality system design in a short time has become difficult. So I wanna introduce high-level synthesis. HLS is one of the solutions to improve design productivity of hardware design. HLS can synthesize HDL code from behavioral description with a programming language such as C or C++. One of the contributions of HLS is the abstraction level of design becomes higher. Statement of program code will be synthesized to the state machine. And also, values and arrays are expressed as register and memory on FPGA. There is two major tools for HLS. Xilinx Vivado HLS is based on C++ tools. It is required to use Pragma directives to optimize the hardware design. Second is Intel SDK for OpenCL compiler. Its policy is the employment of OpenCL library. However, it is essential to understand Pragma directives and OpenCL libraries deeply for deriving optimized hardware. HLS is not only C++, but also various programming languages. Chisel is Scala-based HLS tools. Chisel is employed to the construction languages to the RISC-V processors. Crash is Haskell-based. And also, Carta is original DSL. Synthesizer is Java-based. Pycoran, Polyphony, Python-based. Marbury is Ruby-based. And Octopus is OCaml-based. These HLS tools is developed by Japanese HLS friends, my friends. What we want is, we want to design hardware by Elixir. I want Only me? No? So we want to operate hardware from our Elixir code. If it can be realized, your Elixir application can accelerate, can improve the performance and and power savings. So next topic is the concept of Cockatrice. What is Cockatrice? Cockatrice is summoned beast that appeared in Final Fantasy IV. Do you know? I like Final Fantasy IV. Yeah. The effect is to make all enemies to stones. So your Elixir code can be stoned, synthesized to hardware by Cockatrice. So Cockatrice is a hardware design environment with Elixir. There is two features. One is the Cockatrice synthesizes Elixir Zen-styled code to the description of hardware circuits. Second is Cockatrice provides communication interfaces between Elixir code and hardware circuits. So your Elixir code can be accelerated and low-powered. So what is Elixir Zen-style? Elixir Zen-style is the example code of Elixir Zen-style is like this. Enum is a powerful library to transform data directly. Flow can realize parallel processing by map-reduced model. Pipeline operator can express data flow directly. Zen is Japanese. The meaning of Zen is that essential beauty. The reason why we think its code is Zen that essential programming is the data transformation. So Enum, flow, and pipeline operator describe only data transformation. So we want to consider process model of Zen-styled code. First of all, Enum library, toList, and sort is located on the last steps. And next, we observed the flow library. It means that the full function and negative function are located located with full parallelism. And then pipeline operator means that data flow like this. So I observed its process model. It is similar to efficient hardware architecture. So we summon Cockatrice to break Elixir Zen-styled code as parallel hardware circuits. Okay. This is a systolic array architecture on FPGAs. So full function, 4 full function and 4 negative function can be located on the FPGAs. However, there is enough space on FPGAs. So I can locate the full and negative function like this. And more full and negative can be located. So we can realize hyperparallelism on FPGAs. So next, I explain the hardware description by Elixir. It is an example code of hardware description by Elixir. As you can see, it is completely equivalent to native Elixir code. Cockatrice will treat the def Cockatrice part as hardware description. So you don't need to consider hardware design, and more, its code can be verified at functional level by software. Since we assume software-hardware cooperative systems to apply the Cockatrice, hardware module can be called as same as software function. This is a synthesis flow of Cockatrice. First, metaprogramming method is applied to derive ST of Zen-styled code by quote function. We can analyze Zen-styled code to the AST, convert to the AST. Next, we provide the template of HDL code that are equivalent to Enum function as DSL. The reason why we provide the template DSL file is that Elixir has pattern matching features. So we can synthesize hardware modules by applying pattern matching with AST and DSL. Next, each module is connected as data flow from AST representation of pipeline operator and flow library. Finally, data flow and parallel processing hardware circuit is synthesized. Communication interface and its device driver are automatically generated as new functions. Finally, logic synthesis and compilation of software is applied by respective tools. This slide shows the software-hardware communication interfaces in detail. There is two features. One is activation and operation to hardware from Elixir code. Second is data communication between software and hardware efficiently. We used Elixir 4 bus on Zinc to realize these features. And more, we implement device driver as CNIF modules. Internal of device driver, we employ UDMA buffer. UDMA buffer is a Linux device driver that allocates memory blocks in the kernel spaces as DMA buffer, and user space I/O. So our target is Xilinx Zinc platform. Zinc 7000 is a mid-range class, embedded mid-range class family. Zinc 7000 has a dual-core ARM Cortex-A9 processors with FPGA. Processor and FPGA is connected by ARM AXI4 bus. Second target is Zinc UltraScale Plus family. It is a high-end embedded. It is used for the high-end embedded systems. UltraScale have quad-core ARM Cortex A53 processors with FPGAs. So, demonstration time. I used ARPANET Ultra 96 V2 board. it has a Zinc UltraScale Plus board, UltraScale Plus LSI. In this LSI, 1.5 gigahertz quad-core ARM Cortex-A53 processors and 16 nanometer programmable logics. The reason why I choose it is that the cost. Cost is important for the embedded developers. So we employ the EDA tools as Xilinx Vivado 2019.1. Software platform. For the software platform, we used the Linux kernel version 4.19 with Debian 10 root file systems. Elixir version of Elixir is 1.91 and Alan is 22. Oh, sorry. Okay. I connect this board by JTAG UART. So I log in this board. So, sorry. I want to explain the demonstration code. Demonstration code is very simple. This is a code executed as software. This function is from NML flow libraries and Enum to sort library. Second is hardware version of this code. I'm sorry, I cannot demonstrate the synthesis flow of Cockatrice because synthesis time is very long. So I will demonstrate the interface part of Cockatrice. So this is the code of NIF driver and device driver written by C. So first of all, I load the kernel module of UDMA buffer. Oh, sorry. Try again. Okay. And next, I run the Elixir with Cockatrice. So first of all, I generate the list of So 10,000 element. Each list has 10,000 elements. And then I will execute this function as software. So each element is converted as a negative value. So next, we execute its function on hardware. So is it same result? Okay. So it's my demo. Thank you very much. So finally, I want to discuss the possibility of our research project and share future directions. First discussion point is currently we just implement prototypes. We will publish them as hex packages very soon. Currently, and more, currently supported features are very limited. In other words, we only synthesize Zen-styled code to the hardware. So another Elixir ARM process models, such as task, Gen server, and so on, are suitable for efficient hardware architecture. I want to discuss this point. And also, quantitative evaluation of our proposal will be also important because I am a researcher and to verify academic contributions. Next discussion point is applicable range of Cockatrice. I think applicable range of Cockatrice is not only embedded, but also HPC computing. The reason why I think so is that bigger data for Cockatrice would be suitable since there is some overhead software-hardware communication. And also, AI/ML would be a killer application for Cockatrice. Big data streaming processing for IoT and cloud processing that allows users to change functions flexibility is a good example for Cockatrice. So we are planning to support large-scale FPGA boards with communication interface for PCI Express bus connections. So by the way, I love NAPs. Oh. Experience at Lone Star for me is very good, very great. I made a presentation to promote the innovation of NAPs to Japan at ARAN and Elixir Fest 2019. This is a Japanese slide. The title of my talk on this conference is a new era of IoT development with Elixir pioneered by NABS technologies. And also, I hold the NABS training in Japan by providing the training materials from Frank and Justin. He agreed to hold the NABS training in Japan. Kochi EX, Kyoto EX, Fukuoka EX, and Tokyo EX. So thank you very much, Justin and Frank, to your support. So this is the final slide of my presentation. Future direction of our research project is what will happen when NABs meet Cockatrice. If its dream comes true, NABs project will gain the FPGA power by the Cockatrice. So please help us to evolve the new era of IoT development with Elixirs. So thank you for the attention.